In this section, we are going to study the most important equation, fundamental equation in quantum physics, Schrödinger Equations. On atomic scales, a particle such as an electron cannot be described simply as a point. Instead, we use a wave function to describe the state of a particle. So, wave function is expressed psi, is a function of the position x, y, z, and times. Actually, this is a little bit weird, but it's a complex function. Complex function is expressed a plus bi. And a and b is a real numbers. And the I is the imaginary numbers. Square root minus 1. So as I explained, C is expressed A plus BI. Then complex conjugate is expressed A minus BI. So magnitude is expressed C times complex conjugate. So this is A square plus B square. This is the meaning of the C squares. So this becomes real numbers and positive numbers. If you take squares of the wave functions times dV is a small volumes, this means the probability that a particle will be found at time t within a volume of dV around the point x, y, z. So if you integrate over the all space, so this becomes 1. Because we need to find a particle somewhere in the universe. Okay, so this dV integration means we integrate over the universe. To describe the time evolution of the wave functions was developed by the Armin Schrödinger in 1926. This is the equation to describe the evolution of the wave functions. So Schrödinger equations plays the same central role in the quantum mechanics as do the Newton's law in mechanics, F equal ma, and Maxwell's equation in electromagnetism. So now we'd like to solve this Schrödinger equation in some situations. But first of all, we'd like to explain a little bit technique, how to solve the Schrödinger equation. Separation of variables. Consider the solution that is a simple product of a function of x alone and a function of t alone. So wave functions is expressed the product of the two functions. Lower case of the psi is a function of x. Lower case of the phi is a function of t. So if you consider the partial derivative with respect to t, psi can be placed outside of the derivatives, but because the psi, lower case of the psi is a function of x. And the second derivative, also phi, lower case of the phi is a function of t. You can place the phi is outside. And then you can substitute into the Schrödinger equation. Schrödinger equation is IH bars. Round capital Psi, round T is minus H bar squares over 2m's. Then substitute. Then it becomes next line. Then you can divide it by the phi and the lower case of the psi. Then it becomes next line. These equations. Then if you look at these equations, actually the left hand side is only the function of the t alone. And the right hand side is a function of x alone. Without changing of the t's, you can change the x. Or without changing the x, you can change the t. So it could change the each term separately. So to satisfy this equation, only the one possible way is each term has to be the constant value. Okay, so we have from the single equation, we have two equations. From the first equation, these equations, you can find this equation. So you can easily integrate these equations. So this becomes d phi equal minus h bar over I e dt. So from these equations, log phi equal minus I over h bar et plus integration constant. So phi is some integration constant exponential minus I e t over h bar. So we choose just the integration constant is once. We have this equations. For the another pairs of the equations, we have another differential equations. Then we consider a special case of the stationary state. If the particle is in a state of the definite energy, the probability to find the particle at each point is independent of times. A state with a definite energy is called a stationary state because the particle's probability function does not change with times. For particles in a state of the definite energy of E, these equations we have. So we don't know the lower case of the psi, but we have already solved the equation for the phi, this equation. So you can substitute for this forms here. Then it becomes psi exponential minus I e t over h bar times psi complex conjugate. Complex conjugate of the exponential I e t over h bar. So these two terms should be cancelled out. It becomes 1. So only the lower case of the psi and the complex conjugate. So this is independent of t time. So it becomes a stationary state. So in a stationary state, the wave function probability functions becomes independent of time. So special case of the wave equation for the free particles. So in this case the U is 0. Potential is 0. So in these situations, Schrödinger equation minus h bar squares over 2m's second derivatives with respect to x equal E phi. So in the case of the free particles, E becomes kinetic energies p square over 2m psi, or p 1 over 2m. P is expressed h squares over lambda squares psi. So we use from the here to the here, we use the energy is a kinetic energy, and from here to the here, momentums h over lambda. Okay, so finally, from this equation, you can find second derivatives. becomes a 2m is going to be cancelled out. So minus 2 pi over lambda square c. So this is minus k square c. So k is a wave numbers, 2 pi over lambda. So we use this equation. So finally, we have a differential equations, second derivatives, because minus k square c. So solutions of this equation, c could be exponential ikx or exponential minus ikx. So we have two possibilities. Okay. So equations, wave equations can be expressed exponential ikx for the stationary waves, exponential minus iet over h bars. So by combining these two equations, we have these expressions. From the here to the here, we use the Euler equations. Euler equation, Euler formulas. Exponential I theta could be expressed as trigonometric function cosine theta plus I sine theta. We use this equation. So exponential I kx minus omega t is expressed a cosine kx minus omega t plus ia sine kx minus omega t. If you choose this b, stationary wave equation is expressed with the trigonometric function of the a cosine kx minus omega t plus b sine kx minus omega t. So if you remember the equations, positive k correspond to the wave moving toward the x direction, positive x directions. Negative k correspond to the wave moving toward the negative x directions. But sometimes the particle is localized. Its locations of the particle is confined to some regions. So we'd like to create a localized wave function. How can we create such a localized wave functions? So this is what we call the wave packet. So if we consider two waves of the cosine x and cosine 1.1x, so consider the sum of the two waves. Then the result is this one. You could find out these kind of the waves. So sum of the two waves give the lumpy characters. So particle position is confined in these regions, and there is small probability to find the particle between these two regions. Particle represented by the lumpy wave function is more likely to be found in some region than others. The particle is localized because the c square corresponds to the probability to find the particles. Okay, this is the end of this session.